Hello everyone, my name is Filippo Piersimoni and today's project is about magnetic field lines visualization in a three-dimensional virtual environment. So I made the whole project and the algorithm using Blender. So the script is written in Python. But before starting to look in depth at the algorithm, I'd like to highlight the two main hypotheses behind the whole project, because thanks to this experience I've learned that starting from right hypothesis is essential in order to get to right conclusions, which may sound obvious, but it's definitely not, and you will understand it better throughout the video. So talking about hypotheses, the first hypothesis is the first elementary Laplace equation. I actually don't know how you call it in English, but it doesn't really matter. Basically, the first elementary Laplace equation is an extreme powerful mathematical tool in order to compute and evaluate the magnetic field in a certain point given a certain set of conductors. So let's say that you have a generic wire which represent a one-dimensional conductor, and let's say that this wire is characterized by a certain value of current intensity I, which is constant in time and uniform throughout the conductor. So basically, first Laplace elementary law says that the infinitesimal term of magnetic field, the B, is equal to a constant which differs from material to material. So if you work in an empty space, you will likely use mu naught constant value multiplied by the current intensity value I, which is constant. So we are talking about magnetostatic system and not magnetodynamics. So this means that for the moment we focus on conductive current rather than on displacement current. And then we have the last term of the equation, which is the cross product between the S and mu r divided by r squared. So let's define briefly all these terms. So basically you have to choose a point in the space where you want to evaluate the magnetic field. So let's say that this is our point P. The first elementary Laplace equation tells that the infinitesimal term of conductor, so in this case we are working with a wire, and you can describe an infinitesimal section of this wire that we can represent with this little drawing. So you have that this infinitesimal term gives a contribution that is equal to a constant multiplied by the value of the current intensity, and then you have this cross product, which is the most interesting part of the equation, because it gives you all the geometrical information you need. And there is a cross product between ds, so this vector is basically this vector right here. So it's a vector which has the module equal to the length of the infinitesimal term of conductor, so the infinitesimal part, and the direction and orientation is equal to the one of the current intensity. And then you have the last term, which is mu r, which is a versor, and it is referred to the radius vector, which is the vector that links the infinitesimal term, ds, to our point P. So this will be the radius vector, and so the versor will be equal to the vector divided by its module. So this is the versor. And you do the cross product, and you end up having a result similar to this one. And if you do this computation throughout the conductor, you basically can sum all the contributions given by the infinitesimal term of conductor, and you end up having the global total magnetic field vector in a very point of the space. So the global result will be something like this. We can assume. So the point is that the first thing that is interesting to underline is that this is not the only equation, the only expression of Laplace first Laplace elementary law. There's actually another expression which is more generic and gives you more information. And so the other expression says that the infinitesimal term of magnetic field is equal to the constant, as always, multiplied by the current density vector J, cross product between J and mu r over r squared. And then you have the infinitesimal term which is referred to the volume of the conductor. So in this case, thanks to this second expression, it is more generic because it actually works with the current density vector, vector J. So you have more information about current because thanks to current vector J, you know how the current is flowing throughout the section of the conductor and not only the length of the conductor. So this more generic expression is the one you have to use if you want to work with conductors characterized by multiple dimensions. So, for example, I'm talking about planes, conductive planes, or more generic conductive volumes. But I've shown you this expression first, so the simple one, we could say, because actually the algorithm and the old project is about this very expression, because I wrote and developed the algorithm in order to evaluate the magnetic field created only by wires, which are by definition one-dimensional conductors, one-dimensional mathematical objects. So therefore, you can work with this expression, which clearly is easier to compute than this one. So this is the first hypothesis. The point is that it's extremely useful, and it is clearly at the basis of the old project if you want to draw a magnetic field line or whatever. The point is that of course it is a mathematical tool, and if you want to work with this kind of formula, you have to abstract the problem. Because basically this formula says that the infinitesimal contribution is equal to this equation, but the global finite result will be equal to the integral of the differential of the magnetic field differential, the B. And normally a computer cannot do this kind of operation in general, because computers by definition can't abstract. So therefore, if you want to do a simulation or a generic representation of a magnetic field or of any other kind of stuff which is related to mathematics, you have to discretize the problem. And in the very moment you discretize something, something that originally is continuous, you will definitely end up doing an error. And it's essential to find a way that allows you to evaluate this error. So in order to do this, I needed a second hypothesis. So the second hypothesis is the common knowledge that magnetic field lines are always closed. So you probably remember hearing from school that starting from a generic point of the space, if you try to draw the magnetic line, it will have a certain shape, but sooner or later it will end up closing itself. So you will end up in the same point you start the drawing. This assumption, this hypothesis, in general is completely wrong, which may sound strange in first instance, but you will understand it better viewing the video. So for the moment, just remember this fact. And of course, this doesn't mean that they are always like open. It only means that in general, given a generic conductor with a complex shape, the magnetic field lines are not closed. Of course, if you work with extremely simplified systems, such as a perfect planar loop as a conductor, then magnetic field lines in that specific case will be actually closed, but they are not in general. So this is actually the real interesting thing about this project. So the fact that I started from two hypotheses, assuming that they were both correct, because it was the only thing I could do. But in the end, they turned out to not be both correct, because in the end I found that basically the two hypotheses were describing two different realities, so two different mathematical systems, which was pretty astonishing. So saying that, I think that you have all the tools needed to understand the project. Before starting and before jumping into the in-depth analysis of the algorithm, I just want to tell you that the video will be divided into two parts, two main parts. So the first one, which will start in a few seconds, is about showing you how the algorithm interacts with the virtual environment. So I want to show you how to shape a generic conductor, a generic wire in Blender, and how the algorithm associates a certain value of current intensity to that very conductor. Whereas the second part of the video, which is probably the most interesting one, is about analyzing all the methods that I've implemented in order to actually draw the magnetic field line starting from a generic point of the space by reducing the error accumulated by the discretic representation of the line. So let's get started. So here we are in Blender. Let's say that you want to create in the virtual environment the conductors that you designed in order to study the magnetic field created by them. So of course, as I said before, the algorithm works only with wires. So let's shape a wire in the virtual environment. So first thing first, you have to add a starting mesh. The starting mesh can be whatever you want actually. The important thing is that in the end, after all the modification you do, you get a wire, so a dimensional element, and so that you don't get a plane or a surface or a volume and so on. So in this case, let's for example add a circle, and I will give him let's say 8 vertices. So this is our starting mesh, and from this mesh we want to modify it in order to get the shape of our conductor. So if I move to the edit mode, you notice that you can see and you can read for each vertex a little number. So in this case here you read 0, this one is vertex number 1, and so on. So each number is actually the index associated to each vertex. So in this way I can look at what the software actually look at. So for the software, the vertex number 0 is this one. So if I ask to the software to move vertex number 0 in a certain point of the space, he will move this very vertex. And the same goes for vertex number 1, number 2, number 3, and so on. So knowing this, knowing the way the software interacts with these objects is essential in order to develop the algorithm. Because the point is that, as you may know, when you work in Blender, you start from a basic shape with a starting shape. So in this case with a starting mesh, and then you do a bunch of modifications in order to get the final result, so in order to get the shape you want. So let's say that for example you want to cut this edge right here so that you get a new edge. Then you move this one, and you do the same for this one, and this edge you move it right here. Then you decide to delete this edge, this vertex, and you decide to create a new edge between these two vertices, and so on. So you can do a lot of these steps, and of course you modify drastically the original mesh. So the point is that if now I look at all the vertices, you clearly see that they are not oriented. So you start from, let's start from vertex number 0, then you have a vertex number 1, number 2, number 7, number 10, number 9, and so on. So for the computer, this is not a problem at all. It is designed to work in this way. It is a problem for us because we want to transform this mesh and to work with this mesh as if it was a conductor. So a conductor and a wire characterized by a certain value of current intensity. And this current intensity will move and will flow through the conductor in a certain direction. So what we want to do is to get a new object which has the same shape of this one, because we made all the operations in this mesh. So we want to get the very same shape, because this is the shape of our conductor, but we want a new object where we have the same shape, but where all the vertices are oriented in the same, following the same direction, so that they describe the same direction of the current flow. So now let's just delete this edge and let's do this kind of operation so that we actually work with a closed wire and not with a generic loop. Alright, and here I will run the first function and let's see what happens. So remember that this is the shape of our conductor, and we want to order the vertices. So let's move to scripting layout, and here we are with the first function, source orientation. And yeah, now let's name this object. First of all, let's move it into environment collection, and let's name it in this way. So this is the in Italian, it is translated in Italian, and it means wire that we want to give an orientation. So here we rename it, and now let's run the algorithm. So we get a new object which is called oriented wire. As you can see, oriented wire has the very same shape of the original object, but if we move to edit mode, you can see that now all the vertices are oriented. So you start from 0, then you have 1, 2, 3, 4, and so on, 5, 6, 7, 8, 9, 10, 11, and so on, which is great, which is exactly what we wanted to get. Now if this was the original mesh, so let's just move it so like this, so that we can appreciate the differences. So as you can see from the object viewport, there's no difference at all. The shape is the very same, which is great. But if we move to the edit mode, you can see that the oriented mesh has oriented vertices that go from 0 to 11, whereas the original mesh doesn't have any kind of orientation. So you go from 0 to 1 to 2, 8, 11, 10, and so on. So saying that, this was the first function I implemented, and let's move to the second one. So the second function is about source partitioning. It doesn't change, in this case it doesn't change the order of the vertices, but it actually increases the definition of the source so that the depth of the scan process is higher. So the point is that this function is essential because it actually gives you the link between the computer and so the discretization process behind the algorithm and the first elementary Laplace equation. Because as I said in the first chapter of the video, the first elementary Laplace equation describes relationships between infinitesimal terms. So you have that equation is valid for an infinitesimal term of your conductor. Of course, in using Blender, working with a computer, you can't work with infinitesimal stuff, but you can approximate the output to the correct one by working with very small elements. So very small elements that in the end will likely approximate to an infinitesimal term. So what I'm saying is that if you get this result, actually the second one, which is already oriented. So this is the result you get from the first function, which is about source orientation. And in this case, you can see that this object is pretty large. I mean, it has like 2 meters by 2 meters and of length, and each segment it's pretty long. We are talking about several centimeters for each segment. So it's pretty clear that you can't just start computing and evaluating the magnetic field by implementing the first Laplace elementary equation, considering starting with this object, because you have that the edges are too long in comparison with the global dimension of the loop of the wire, so the conductor. So you basically want to implement a function which doesn't change the shape, because we always don't want to change the shape, because the shape is the first thing you define, and you want to work with the same shape for each step of the algorithm. But so you don't want to change the shape, but you want to increase the definition. Let's say the definition, so the number of vertices of this object, so that in the end, when you finally implement the first elementary Laplace equation, you get a result which is close to the correct one. And remember that the correct result, you can get the correct result only working with mathematics and by abstracting the problem. So let's move to the scripting viewport. I want to work with this object. So let's move to scripting, source partitioning function. So in this case, I have to rename the object in this way. So let's copy and paste the name, and here it is, and let's move it to the environment collection. Then it's also important to put the cursor to world origin and actually apply an all transforms Control A command. And here we need to define this parameter. So we have a flag parameter which is called source partitioning, and of course I put it in true because we want to do a source partitioning process. And then you have this other parameter which is essential, and it basically tells you the average length of the edge that you want to get in your partition. So in this case I put it equal to 10 centimeters. Of course it is expressed in meters. So yeah, we can try a first try. So starting from this object, and let's run the function. Right. So we get a new object which is called partition wire, As you can see, again, we have the very same shape as before, but if we move to the edit mode, you get a much higher definition of the scan process of the source, which is essential in order to implement the first elementary Laplace equation. So let's move it again a bit higher so that we can appreciate the differences. Now I just want to do another try, another attempt by working with a 1 centimeter source partitioning standard value, just to see what happens. And we get this new object. Let's move it upper. And let's move to edit mode. Sorry. What happened here? Alright, so this is the one we are interested in. Sorry for the misclick. So let's delete the wrong one, which is the other one, and this one. And here you can see that the definition is going pretty extreme, and now you are working with higher definition, better quality of higher quality of the output, and of course more computing steps to do, clearly. So I think that you can easily understand the importance of this function. And with this, thanks to this function, we are at the end of the first part of today's project, which was about briefly showing you how to shape the conductor and how the algorithm interacts with the virtual environment. And now we can move to the second part, and we can start talking about the methods behind the drawing process of the field lines. So here we are with the second part of the video, and finally we can start talking about the methods which allows the drawing of the magnetic field line starting from a precise point. So the first method I want to analyze is the elementary method, and I called it elementary because it is probably the first solution you can think about in order to solve the problem. So before analyzing the elementary method, I just want to tell you that in this chapter and also in the next one, I will analyze the system and the problem starting from this kind of wire, which is a loop, so a perfect circular wire. But in this case, I made this choice because in this way, considering this specific shape of the conductor, I can easily you already know actually how the magnetic field will develop, because it is an easy a simple object to parameterize and to study. So it helps me a lot in explaining you all the methods. I just want to remember you that in general magnetic field lines are not closed, but of course in this specific case, so if you work with a perfect circular wire, then its magnetic field lines will be closed, because you are working with a specific and also specific conductor, specific system, which is a simplification of all the possibilities you can work with. So saying that, let's jump into the elementary method. We have our loop, and this is just a drawing of the magnetic field lines development that you probably already know from student's book. So in this case, I considered a current which is flowing in this direction. So you have actually a counterclockwise direction, seeing the system from the front view. And I defined these two parameters. So the first parameter is just the radius of the wire, whereas the second one stands for the standard field line length, which is equal to, in this case, 10 centimeters, but don't mind about these numbers, they are just an example. So standard field line length is basically the average length of the polygonal object that the algorithm creates in order to represent the magnetic field line. So let's talk about all the steps of the elementary method. So you start from a generic point of space where you want to so from this point you want to evaluate the one and only magnetic field line which it belongs to. So this is our point P, which is our starting point. And then the elementary method is basically an iterative method that is all about evaluating the total magnetic field vector in this precise point, given a finite set of sources. So let's say that the total magnetic field vector is something similar to this one. So this is our total magnetic field vector B, and then the algorithm does a translation of this point following the direction described by the vector B, and the translation is equivalent to this value, which is our parameter, standard field line length. So this means that in this case I put it equal to 10 centimeters, so it will be something like this. Let's say a tenth of so a fifth of this one. So this is our the end of the translation. So let's call it Q. And this is the second point of the polygonal. Then you repeat this loop for as long as you want. Of course, you have to put a stop to the algorithm. So starting from Q, you will define the third point, the third vertex of the polygonal by evaluating the total magnetic field vector, which will be like this, and then you translate Q of a segment equal to actually of a movement equal to 10 centimeters, and the direction described by the magnetic field vector. So you end up here, and we call this S. And then you go on following this method for as many vertices as you want. So you have PQ, actually I called it S, but I wanted to call it R, and then you have S, and so on. for as long as you prefer. So this is the first method. As you can see, the result, the output, is something that in a way or in the other is following the direction, the three-dimensional development of the magnetic field line. But as you can easily see from this simple drawing, you are accumulating an enormous error. So you are you're not describing the same field line, because every time you do an iteration, every time you define a new vertex, and every time the magnetic field changes orientation locally, so close to the point, which is a characteristic, an extremely common characteristic of magnetic field lines, you end up in a point which doesn't belong anymore to the original magnetic field line, but this new point that can be Q and then R and then S will belong to another magnetic field line that presumably is close to the original one, but it's not the original one, it's not the one you want to represent, and of course this is a problem that you need to solve. But before looking at a method that reduce this error in an extremely well by an extremely positive way, I just want to show you the method in Blender. And here we are with our perfect circular loop. So in this case, if we move to edit mode, the loop, the circle, is made up by of 64 vertices, actually 64 edges and 65 vertices to be precise. And so in this case I want to do a few attempts. So let's move to script. I just want to show you briefly how the algorithm manage all the sources of the scene. So basically you have this dictionary right here, current dictionary, where this key is the name that you give to each sources of your scene. So in this case, this one is the source named S4, source number 4. And of course you can put in your scene as many sources as you prefer. In this case you have, as you can see here, 10 slots, but you can add easily other one. So in this case we want to work and we want to evaluate the magnetic field created by source number 4. So let's bring to 0 the current intensity value associated to all the other sources, such as S3, which is the only one that was different from 0. And here we have that source 4 is equal to 10. We can put it in this case we can put whatever number we want, such as 6 amperes. Of course this number describes the intensity of the current which flows in the conductor. Then we have other important parameters to look at. Source partitioning. I want to start with a false value for source partitioning, because I think that 64 edges for a circle of this type is already a good number of is already a good value of discretization and of partition in order to draw the fill line. But don't worry, I will, in other attempts, I will try to work with source partitioning, so we will bring it to true value. Then we have source partitioning standard, which is pretty useless if we put it in false value. Then we have field line standard length, which is the famous parameter you have just seen in the previous chapter. So in this case, it's equal to 10 centimeters. So again, let's don't modify it here in this moment. I will modify it later on. And then we have the last parameter, which is max field line length, which tells us how many edges we want to. It tells us the number of edges we want to draw in the polygonal representation of the field line. So in this case, it's equal to 600, but let's put it equal to 100, and then we can modify it whenever we want. So now the last thing I wanted to tell you before running the function is that the algorithm draws the line, the magnetic field line, starting from the position of the 3D cursor you see right here. So I can move it wherever I want, and it will draw the line starting from here. And just so that you know, in this case the current flows from from vertex number 0 to the end. So in this case it flows from here to here, so it follows a counterclockwise direction from this point of view, but that's not that relevant for the moment. And let's draw the first field line representation with the elementary method, and let's see what happened. So S4 equal to 6 ampere, and let's run this algorithm. Alright, this is the first representation we get. So as you can see here, we definitely have a certain value of a certain error accumulated by the representation of the field line. Remember that we are still working with the elementary method, which has a pretty high error value associated to it. And because also you know that in this simplified case, working with a perfect circular shaped loop or shaped wire, the magnetic field lines are actually closed. So there's definitely a certain error right here that starts from the very beginning. But in this case, you also see that the definition of the polygonal is pretty low, right? So you can see that you have a very edgy shape of the polygonal. So let's do another attempt by reducing these parameters so that we get a higher definition of the representation of the field line. So I will bring it to 0.05 meters, and let's see the impact that this change has to the representation, just to the output. So this is the second output. As you can see, the error is much less. It has been reduced by a lot. In this case, this is the maximum we can get because we didn't multiply this factor. So if I put 200 instead of 100 and I delete this object, then you get this output, which is more representative of the problem. So in this case, you can see that by reducing by a factor of 0.5 the length of the polygonal of the standard length of the polygonal, you reduce the error. Of course, you still get a certain error because you're working with the elementary method, but still the result is pretty, I would say, already pretty realistic. And yeah, let's just try to move the cursor in another position and see what we get. So again, let's work with the same parameters, and this is the second output, which is similar to the other one, which is right. And yeah, just to finish this chapter, let's see what happens if we put the cursor at the very center of the system. So in theory, we should get a straight line, and let's see if it is correct. So cursor to world origin, we are in the very center of the system. And let's run the algorithm, and we actually got a straight line. So the algorithm is well written, and it is describing pretty well the physics behind the problem. Yeah, I think that this was all for this chapter, and let's move to the second method. So let's talk about the osculating circles method, which I personally consider as one of the greatest intuitions behind the project. So this is the second method I implemented, and of course it comes after the elementary method. So in this case, we have, as always, I will do the explanation considering this system, so considering a perfect circular loop, but remember it is a specific system, not a generic one. So let's consider the same system as before, as I did in the chapter before. In this case, you can see that let's say that you are implementing the elementary method, and you define these three vertices. So the first one, P, which is our starting point, so by definition it belongs to the magnetic field line you want to represent. Then you have Q and you have R. So you have three vertices and two edges, and you can easily associate to each of these edges a vector. So a vector that goes from P to Q, which is our first vector, and then the second one which goes from Q to R, which is the second one. So here, what is the osculating circles method about? It is basically about assuming that locally the field is concentric. So as soon as you assume that it is locally concentric, which is of course an approximation, but it helps a lot to reduce the error. In the very moment you assume it is concentric, you can create this kind of geometrical construction. So as you can see here, thanks to the elementary method, we defined these three vertices and these two vectors associated to two edges. So this means that you know the length of these two edges, because the length of these two edges will be equivalent to the standard field line length parameter you have just seen in the previous chapter. So these two vectors have same module, same length, and then you can also compute the angle, which is this one. So the angle between the two vectors, because you can compute it thanks to the cross product property, because you have that in general cross product between two vectors is equal to the product between the modules multiplied by the sine of the angle between them, and therefore you can easily get the angle between them using the arcsine function. And so it's a very easy calculus. So you have this information, so you know this length, PQ segment length, and you know this angle value. So these informations are the one you need in order to evaluate this error right here. Because the idea behind the osculating circles method is that if you approximate the local development of the magnetic line as a concentrical development, which is again an approximation, but in all the cases is an extremely valid approximation. If you do this kind of assumption, then you can calculate, you can compute the length of this translation, which is the translation you need in order to bring the Q, so the second point Q, to this field line, so this one, which is the field line that belongs to P. Actually, P belongs to this field line, so it is the field line you actually want to represent, because it's the field line associated to the starting point that by definition belongs to its field line, right? So you understand that this method is extremely powerful. Now let's just do some brief trigonometry calculus. So you have that this segment right here, AP, which is the quantity that you want to compute, because AP, if the two circles are concentric, AP will be equal to Q, let's say QB, which is this point. So AP is equal to the radius of AO, which is the radius of this bigger circle, minus AO, so the radius multiplied, which is also equal to OQ, multiplied by the sine, actually the cosine of this angle. So let's call this angle theta, which is also this one and also this one, thanks to trigonometry. So we have AO minus AO multiply cos theta, so which is equal to AO 1 minus cosine theta. So now the point is that we don't know much about AO, but we can express this radius of the bigger circle in function of this element PQ, and we know the value, so the length of this segment, because again it is the standard field line length parameter we defined at the beginning of the code. So you have that AO. Actually, let's say that the sine of this angle theta by definition is equal to the opposite edge, so PQ, divided by the radius, so the hypotenuse, I don't know how you call it in English, but this quantity right here. So OQ, and therefore OQ, which is equal to AO, is equal to PQ over divided by sine of theta. And so now you end up having that the AP, which is the length of the translation you want to do in order to bring Q back to the original feed line, is equal to AO, so PQ, which is the feed line length standard, divided by sine theta, multiplied by 1 minus cosine theta. And you have all the information you need, and therefore you can actually evaluate this value right here. So you can evaluate the length of the translation, and then you can also easily compute the direction, so the vector associated to this translation. Because, for example, you can do the cross product between these two vectors, so you end up having something like this, and then you can do the cross product between this result and the second vector QR, so you end up having something like this, which is pointing right in the middle, in the origin, in the center of our concentrical system of circles. So this is actually the essence of the project. So I called it Osculating Circles method because clearly it has a lot in common with the osculating circles idea, which of course belongs to another field, but it has a lot in common with this system. So now let's jump into Blender so that I can show you in a much clearer way how the method works. So here we are with the same system as before. So our circular loop, and as you can see, I didn't delete the previous representation of the line we made implementing the elementary method because I want to do a comparison between the two methods. So let's move to the same starting point as before, and here we have sources number 4, which is characterized by a current, constant current equal to 6 ampere, and 0 the other one. Alright, I think we are ready. Let's work with the very same parameters. So source partitioning equal false, so partitioning standard equal, it doesn't really matter. Field line standard equal 5 centimeters, which is the same as before, if I remember correctly. And max field line length, let's bring it to 200 as before. Let's run the algorithm and see what happened. Alright, so this is the result, and it's pretty astonishing. It seems it even looks like the magnetic field line is closing. It is actually closed. To be precise, if you zoom enough, you can see that it's not closed because actually the system it's not concentric, although the concentric approximation is extremely valid in order to reduce the error accumulation. So if we zoom in the polygonal, you see that here you still have a certain error, but it is clearly much less than before. So now I just wanted to do other let's try for example to increase the definition of the source. So let's actually work with the source partitioning function. Let's bring it to true value, and so in this case let's see the average length of the edge, which is equal to 4 centimeters. Let's bring it to 16 centimeters. Actually, is it 4 or is it 40? Actually 4. So I want to bring it to 0.02, 2 centimeters. Let's just see what happened with the source partitioning function. Of course, in this case, the process needs a bit more time, but I think that we already have an output. Now it's not easy to understand. All right, it should be this one, because we have this one. All right, this is the output, and you can see that it seems to be the equivalent as before. This is because in this case the source partitioning method isn't necessary because you are working with a simplified system, and therefore you have a lot of symmetries, and therefore you don't need basically to do a source partitioning. Of course, in other systems, in other examples, you will definitely need that function. So this is the result we get. Now I wanted to show you another system which is pretty interesting, because it reveals a strange relationship between these two methods. So let's delete all the objects we created. We don't need them anymore. Let's hide the source number 4. So the conductor I wanted to show you is this one, which has a pretty interesting shape, because as you can see you have here 3 loops that create a little solenoid, we could say, and then you have this shape that closes the conductor. Now if I start to draw the line from the very center of this region right here, let's put these parameters. So let's first work with the elementary method, and let's put these parameters. So source partitioning equal false, fill line standard equal to 5 centimeters, and max fill length equal to 360 edges. So 360. Let's run it and see what happened. Oh, and remember to change the values for the currents associated to the sources. We'll bring it to 10 ampere. All right, I think we are ready. Let's see. All right, so in this case, you see that I told you that it was a extremely interesting example, because it looks like that thanks to the elementary method, this very field line, magnetic field line, is closing actually to itself. So it looks like this error is acceptable, and you may think that the real parameterized shape of this field line describes a line which is closed. But now we are working with the elementary method, so let's implement the osculating circle method that we know is much more precise than the elementary method. So let's move to the other function, 1.4, and let's change a bit the parameters. So 5 centimeters of field line standard and 290 edges for this new representation. And then modify as always the sources parameters, S5 equal to 10, all the other equal to 0. And let's run the script. Oh, I forgot to change the source partitioning parameter. So yeah, it's taking a lot of time, and this could be a problem. Alright, it doesn't take that much time in the end. So you can see that this is even more interesting than I thought, because by I didn't modify this parameter, so it actually did a source partitioning by partitioning the object of this parameter, so an average length of the segment equal to 2 centimeters, and you see that the final result is something like this. It's something like this, which is definitely not closed. It definitely doesn't describe a closed line. And now let's try. I don't want to. Let's try this thing. So let's bring it to false, because it requests too much time. So false, and let's try to increase. First of all, I want to see what happens if we run this by putting a false source partitioning value. So this is the output. Alright, you can see that again, in this case, the source partitioning function doesn't change the representation that much, because the two lines are very similar. But let's see if I let's see what happens if I increase the definition of the polygonal, so of the representation, by using the elementary method. So I basically want to see if the elementary method gets close to the osculating circles method or not. So source no loop optimization. Now let's do something like 0.01, and this one let's bring it equal to 1000, even 1200 could be a good value. Let's run the script. Now we will take a bit of time. Alright, so what do we get? This should be... Alright, so this is the one we are interested in. As you can see, 1200 edges were a bit gives us a short polygonal, so we need to increase this parameter. So let's bring it to let's do this instead, this equal to 600, and let's move the starting point from the ending of the previous representation, and you can easily understand that this kind of workflow is the equivalent of repeating the whole algorithm. Here we are. Alright, and this is the final result we get. So let's sum it up. This is, this was the previous, the very first line, field line, magnetic field line I drew using the elementary method by following certain parameters, and you get this result which is likely to close. So it looks like the field line is defining a loop, so it's closed. Whereas if you use the osculating circle method, you get this result, which is pretty different from the previous one. Then we implemented the elementary method a second time by changing the parameters, and to be more precise, we increase the precision and the definition of the representation by reducing the length, the average length of the field line standard value, so of the average length of the edge of the polygonal. And the result, we got this result. Alright, this was the last result we got. That clearly is closer to the osculating circle representation than to the elementary method representation. So this means that oscillating circle function is again extremely powerful. It allows you to get a precise representation of the field line without losing too much time in computational process by defining thousands of edges. So this was just an interesting system that I wanted to show you, just to try to make some conclusion about today's project. And now let's move to the next chapter. In this short chapter, I just want to show you how you can get a global visualization of magnetic field in a certain volume of the virtual environment. So the point is that so far you have seen that I've always started to draw the line from a so-called starting point, but you can easily imagine that working with the computer, you can define various starting points in the same virtual environment, so that you can get various magnetic field line representations, which of course will be associated to different points in the space. So this is exactly what this function is about. This is basically the generic volume in the virtual environment where we want to do the mapping, so where we want to visualize the magnetic field. Of course, you can change the dimensions of this volume as much as you prefer. Let's bring this to 1.2, for example. And you can also change, of course, the position, right? So like this. Then let's do an example. Let's add our wire, as always, source number 4. Yeah, let's bring the volume in a generic position like this one. Now I move into the scripting layout, and here there are a bunch of new parameters. So let me modify this to like 100, or yeah, 100 could be right. And then you have field line standard. I want it to be a bit higher, like 5 centimeters. The new parameter is the aperture depth. So basically it tells you the length of the edge of the module of the lattice structure that you create in order to define all the starting point that you want to work with. So basically, knowing the dimensions of your volume, which is this one, so 1 meter per 1 meter per 1.2 meters, you decide the dimensions of this lattice structure. So let me show you better what I'm talking about. So if I move to the volume mapping code layout, in this case I can do a lot of attempts, such as let's see what happens if I put this equal to 0.3 starting from this volume right here. Alright, so in this case it generated a lattice, or at least it generated this cloud of points, and basically you can verify that the distance between each vertex is exactly equal to, in this case, 0.3, so equal to the parameter. Let's verify it. Edge length f 0.3, exactly as expected. So in this way, these are your various starting points, and from each of these one you will draw a field line, and of course you will draw it both from one side and also from the other, because field line by definition doesn't have like a starting point and an ending point. It's something more infinite. So I think that 0.3 is a bit low. Let's see if I put it equal to 0.4, how many points we get. Alright, 0.4 could be okay. I will work with 0.4. So 0.4, and let's run this script. Oh, and I forgot to check the current dictionary values. So we want to evaluate the magnetic field created by source number 4, which is this one. Let's bring it equal to 6 ampere, and yeah, let's try now. Alright, this is the result we expected. So as you can see here, the algorithm drew a bunch of magnetic field lines starting from each point that we evaluated thanks to the volume mapping function. So, and this is definitely useful to visualize all the magnetic field in the volume. So let me just do some more examples. So let's delete this. If I, for example, if I add the previous, let's see what happens if now we combine the two effects given by the source number 4 and source number 5. So, and let's bring them both to 10 ampere. All right. We keep this volume reference, and let's run it. Of course, all right. And this is the result, a pretty interesting result. Basically what's going on is that the loop, so the orientation of the current that flows through the loop is from here, okay, it was counterclockwise, so the loop, so this wire, the circle wire, is wants the field to goes up in this direction, right? Whereas this element right here, so this conductor, in this case its current goes from where is 484. Yeah, it's not oriented because we are working in the original mesh, but trust me, the current goes from here to here, so the effect brings the magnetic field line in this direction, and the result is something like this, which is pretty realistic also, just following the intuition. Yeah, that's it basically. And now let's move to the next chapter. So now you may think that the project is over, considering that, as you've just seen, the osculating circle method drastically reduce the error accumulated by the algorithm. But the video is not over yet, because I want to share with you two methods that are still fascinating. Probably they are even more fascinating than the osculating circles method. And the point is that I implemented these two methods in order to define a closed representation of the field line, because you have to remember that at the beginning of this experience, at the beginning of this project, I assumed that both the two hypotheses were correct. So this means that at the time, before actually understanding and having this revelation about the real development of field line, I basically thought that the representation I would get from the implementation of osculating circles method was the fact that the line, the polygonal, wasn't closed. I thought that this fact was only caused by the accumulation of the error, and of course this assumption I made was wrong. But at that time I thought that in general, magnetic field line were closed, so it was the only explanation I could get. So I think that this part of the video is useless in terms of in terms of understanding the physics behind magnetic field and its geometrical development in the three-dimensional space. But nevertheless, I think that it is extremely interesting, or actually it is, at least it is interesting to see how you can sometimes define and came up with ideas and functions, so in this case functions, so methods, which don't describe reality, which are not are incoherent with the hypothesis you made, so in this case with the first elementary Laplace equation. But it's interesting to just to see what kind of solution you can think about and how far you can get from the real representation of reality. So hope you will enjoy it, and let's get into it. Let's start with the most controversial side of today's project. So in this chapter and in the next one I will work mainly with this system. You have two conductors which have different shapes, and I think that it is pretty clear that this system differs from the oversimplified system we have studied so far, which was the system made only by the perfect circular loop. In this case you have two conductors and they have different shapes, so it means that in general, starting from a generic point of the space as a starting point, you will get an open magnetic field line and not a closed one, because the system is asymmetrical, and therefore you get a much more complicated description of the magnetic field. So in this chapter I want to analyze a function that I called the uniform settling function, whereas in the next chapter I will analyze another function, which is the last one we will look at. And let's start with this function called uniform settling method. So the assumption is that magnetic field lines are always closed. Of course, this is not correct, but remember that at the beginning of the project I didn't know it. I assumed it to be correct, because I needed that very hypothesis in order to evaluate the error that the algorithm was accumulating throughout the drawing process of the polygonal line that represents the magnetic field line. So if magnetic field lines are always closed, it means that the error accumulated by the polygonal construction that you can get by implementing the osculating circles method, this error is caused only by the algorithm and the discretization of the system, and it has nothing to do with the physics described by the first Laplace elementary equation. Of course, in reality, the error, which is not completely an error, has a lot to do in common with the first Laplace elementary equation, but let's say that this is not correct. By the way, when I talk about error and error accumulation, I basically mean the distance, the geometrical distance between a vertex of your polygonal and the position it would have if it belonged to the original fill line, So this is what I mean by saying error. Now, just in order to explain you a bit better what I'm talking about, let's work with this system, and I put the cursor right here. So remember that the cursor position is our starting point. And now I will, firstly, I will draw the polygonal thanks to the to the osculating circles method. So let's move to script and let's get the first polygonal. So this is the output. As you can see, this is the result that we get by implementing the osculating circles method. The first thing you may notice is that in the script I put this parameter max fill line length equal to 1000 edges, but it is pretty clear that if we move to edit mode, this polygonal right here, this representation of the fill line, is made of 66, actually 67 vertices, so 66 edges, which of course is smaller than 1000. So basically I wrote a function which detects when the polygonal has concluded the first loop, because you need to detect when you want to stop the construction of the polygonal in order to adjust it, in order to work on it. And basically this function does this kind of operation by verifying various conditions. So in this case, the first loop ends right here at the 66th vertices, and starting from this polygonal, you can work with it, you can modify it in order to reduce the error. So the first thing you have to notice is that if the fill line is closed, it means that, for example, this vertex should be right here at the starting point of the polygonal, because as I said a few minutes ago, if the fill line is closed, the error, the global error that you get is caused only by the algorithm. So in this case, the global error associated to this vertex is equal to this segment right here. So it's equal to this vector, because this vertex likely should be here and not here. So what you want to do is you want to translate this vertex from here to here, so that you can close the polygonal, and so you can reduce the error of the representation of the fill line. So basically the uniform settling method starts from the hypothesis that the error accumulated by the polygonal construction, so by the algorithm, is linear throughout the construction of the polygonal line. So what it means is that moving from one vertex to the next one, you are increasing the error of a constant value. Of course, it is an hypothesis. I don't know, in the most generic case, it's not correct, but it's an hypothesis you need to do in order to move on with the solutions. And if this hypothesis is correct, and it is an assumption, so I assume it is correct. It means that you get the total error, so the global error is the one associated to the last vertex, because if the growth rate of the error is constant throughout the construction of the polygonal line, it means that the last vertex will it means that the error associated to the last vertex will be the higher among all the others. So thanks to this assumption, you have a direct dependence between the position of each vertex and the error associated to them, because you have that this vertex has this error. This vertex will have a similar error, but the error associated to it will be a bit lower to this one, because this vertex comes before the last vertex in the construction process of the polygonal. So to make it short, you basically you start from this vector, which tells you the total error you get at the end of the construction of the polygonal, and this vector is defined relative to the canonic basis. So we are working in the three-dimensional space in Blender, and of course you can define how many bases you want. You just need to get a set of 3 independent vectors, but these all the points are in the space are defined following the canonic base, which means that this vector right here that starts from this vertex and ends into this one is defined in the 3 canonic vectors of the canonic base. So you get the components of this vector, and then while you are creating the polygonal, you define a local basis for each vertex, which I will show you in a few minutes. So you define a local basis for each vertex, or if you prefer a local basis for each edge. And after you got the components of this vector in the canonic basis, you can do a very common linear algebra operation, which is the basis change. So you can describe and get the definition of this vector in the local base of this vertex right here. So after you got these local components, which will be 3 components referred to this local base, you can describe for each local base associated to each vertices, you can describe a vector which has the same local components of the original vector, which is this one. So of the total global error vector. So you can get the definition of these vectors, but of course the vectors associated to these local bases will be shorter than this vector, and their length will depend by the position of the vertex in the construction of the polygonal. So this is the logic behind this function, which is called uniform settling function. And now I want to show it to you, because it gets easier to explain you how it works if you look at the direct output. So let's move to the next script, uniform settling. We will work with the same parameters, and let's run it. Alright, and this is the result you get. So this is the new polygonal, and you can see that now it is closed, of course, because you moved these vertex from here to here following this translation. And as you can see in the output, you can see all the local bases associated to each vertex. So in this case, you basically define this vector in this local basis, so that you get the three local components, and then for each local basis you get the description of new vector which has the same local direction given by the local components of this vector described in its local basis, and the module of all the settling vectors will be equal to the module of this vector divided by the relative position of actually not divided, but similar to the local position of the vertex in the polygonal. And this is the result you get. So I think that it is a pretty astonishing way of solving the problem. The sad news is that it wasn't necessary at all because magnetic field lines are open in general. But if you actually work with a mathematical field which has always closed field lines, these kind of functions and this way of thinking of solving the problem is definitely an interesting one. So saying that, I think that we can move to the next chapter and to the next function. So let's talk about the double tracing method. As you can see here, I want to work with the same system as before. I've only redefined the polygonal, working with a lower level of the average length of the polygonal. So basically, if you remember, in the previous chapter, we work with a feed line standard parameter value equal to 5 centimeters, and this was the result we got, this one right here. Whereas this is the result you get if you work with 2 centimeters. Of course, the output clearly is much smoother than before, because basically the average length of your edges, this one, is less than half the length of the previous edges. But as you can see, the new output is pretty close to the previous one, which is a good sign of the quality of the algorithm. And as always, here you have the drawing, the representation of all the local bases associated to the polygonal created by implementing the osculating circles method. By the way, talking about the double tracing method, so basically you have seen that the uniform settling function is extremely powerful, but it has a main problem. The problem is that in this region right here, so near the starting point, you generally you get strong irregularity of the polygonal. So as you can see here in this segment, so if I consider this part of the polygonal, the drawing is pretty smooth, so it's pretty realistic. But if I zoom in this region, which is here, this is the starting point, you can see that there's a bit of an irregular development of line, because you can appreciate it looking at these two edges, which is the first edges and the last, the first edge and the last edge. So in general, you don't want this kind of output, because most of the time the magnetic choosing a generic point of generic magnetic field lines, you can always define the one and only straight line which is tangent to the magnetic field line in that very point. And this is actually the essence of the first elementary Laplace equation, because it tells you that given any sources, you can always evaluate the unique value, vectorial value of the total magnetic field in a certain point of the space. So you don't want to have this strong irregularity. Instead, you want this to be as smooth as possible. So a possible solution to get this smooth drawing of the polygonal, which is the representation of your field line, is to work with the double tracing method. So basically, double tracing method is about drawing two different polygonals, working with the uniform settling function. So you draw two polygonals starting from, of course, the same starting point, and the difference between these two polygonals is that they are created. They are both created thanks to the uniform settling function. But in one case, you work with a positive formalism. So by positive formalism, I mean that you basically work with the expression of first elementary Laplace equation that you saw at the very beginning of the video, whereas the second polygonal is created by working with a negative formalism. So a negative formalism means that basically you work with the first Laplace elementary equation, but you add a -1 factor to it, so that all the math behind, all the geometrical and mathematical vectorial relationships are inverted, because there is this factor equal to -1. So let me show you the result you get. This was the previous result, that of course this result, we got this result working with a positive formalism. So basically applying the first elementary Laplace equation in the way you saw at the beginning of the video, but by changing a single character in the code, you can work with a negative formalism. So here we are in the function field versor, which is the one that compute the versor in order to do the translation that is fundamental for the algorithm. And here just add a character minus and you get the negative formalism. So if now I run the algorithm, you will get a different result from before, and you get this kind of result. So this is the line created thanks to the negative formalism, and this is the one created thanks to the positive one. Of course, they are different, but as you can see, they in theory they referred to the same field line. So they are representing the same magnetic field line, the one that goes through this starting point. So now the idea behind the double tracing method is that if you start from here, right, and you move to this direction, these first vertices are the one that you created thanks to the positive formalism. So these first vertices will be close, will have very small error because they are close to the origin, and by definition the origin, the starting point, belongs to the field line you want to represent. So the error associated to the starting point is always 0. Of course, the farther you go in the polygonal, the higher the error gets. And the same goes for the other polygonal that we draw following a negative formalism. So in this case, you have these first vertices are have correct position, so their error is pretty low. And the farther you go from the origin, the higher the error gets. So the idea is that as soon as you understand this fact, you can assume that the most correct drawing of the polygonal, so the representation of the magnetic field line which is closer to the actual field line, is the result of weighted sum of the vertices of both the polygonal, so both the positive one and the positive one and the negative one. And of course it is a weighted sum because you are saying that starting from here, these vertices in this region of space, so in this one, in the upper region, the field line is better approximated by the positive polygonal, because the positive polygonal follows this direction, this development. So these are the first vertices that you actually draw during the process. In fact, you can see that this is vertex number 2, number 3, and so on. Whereas talking about the negative polygonal approximates pretty well the field line in this region right here, because these are the first vertices you have drawn. And of course in the middle, so at this level, the result will be an average between the two vertices, something like that. So basically I will show you directly the output without further explanation, and the output is this one. So double tracing, 2 centimeters and 1000 max fill line length value. S2 equal to 10 and S4 equal to 10, and then all the others are equal to 0. Alright, and let's see what happens. And this is the result you get. Again, pretty astonishing stuff. And as you can see, it's clearly the result of a weighted average sum of all the vertices, all the positions of all vertices of both the positive and the negative polygonal. So this is the final output. We started from this system. We wanted to evaluate the fill line that passes through this starting point, and we got this output. And as you can see, this time the polygonal is regular throughout the development, so it is a pretty smooth drawing of the fill line. The problem is that this is not the real aspect, the real development of the polygonal, and I think this whole story is fascinating, because you end up thinking about so many solutions, so many functions, spending so much energy and efforts and so on, and in the end you understand that what they told you at school was completely wrong. And I think this was everything to say about the double tracing function, and also about today's project. So this was everything for today's project. I hope you enjoyed it. Let me know in a comment below if you have everything interesting to say. And yeah, have a nice day and see you in the next project.